Hello again and welcome back. This video lecture covers Chapter 6, Section 3 in our book. We're returning to a discussion of uniform circular motion, which we first introduced, as you know, in Chapter 4 when we were studying kinematics. And to remind you, uniform circular motion is that special kind of circular motion where a particle, as it moves in a circle, moves with constant speed, right? Constant speed, constant magnitude of velocity. So we studied the kinematics of uniform circular motion in Chapter 4. What's new now in Chapter 6? Why come back to it? Now we're studying the dynamics of uniform circular motion. Why does a particle move in a circle at constant speed? And of course, it's still the same physics concept that will answer the why question, Newton's second law. We just have to be careful to apply it correctly. We're going to apply it now to the case of a particle moving in a circle at constant speed. All right, first let's start with a brief review of the most important kinematic concept that applies to uniform circular motion. Let's say we have a particle. It's moving in a circle of radius r, right, at constant speed. Then we know this. The particle's acceleration is directed always towards the center of the circle, and the magnitude of that acceleration is constant. And there's the formula for that magnitude of the acceleration. It's the magnitude of the velocity squared, if you like, the speed squared, divided by the radius of the circle. Okay? And remember that acceleration arises because as a particle moves in a circle, its velocity direction is constantly changing. And if the velocity is changing, in this case in direction, there must be an acceleration. In this case, the acceleration is directed towards the center of the circle, and this is the formula for its magnitude. Speed squared over radius of circle. Now we're just going to combine that kinematic concept with Newton's second law. Because Newton tells me that if there is an acceleration in a particular direction, there must be a net force in that same direction. So there must be a net force on the particle directed towards the center of the circle. And that's just Newton's second law. If there's an acceleration directed towards the center of the circle, there must be a net force towards the center. And that's really all we're going to be saying in this whole section. Has to be a net force towards the center of the circle if the particle is going to move with uniform circular motion. Now, I'll mention this word again that came up in Chapter 4 when we studied uniform circular motion, and it had to do with this directed towards the center of the circle idea. Directed towards the center of the circle. Physicists often use a word when they're studying circular motion and they want to emphasize directed towards the center. That word is centripetal. And so you will hear physicists talking about centripetal acceleration. They just mean uniform circular motion with the acceleration pointing towards the center. And I don't like this, but I can't deny the fact that you'll hear it commonly amongst physicists. They'll talk about centripetal force. I want to emphasize right away, there is no such special type of force in nature called the centripetal force, like there is the gravitational force. Okay? All I'm saying is that according to Newton, if there is an acceleration in a certain direction, in this case towards the center of a circle, there must be a net force towards the center of the circle. Okay? And this net force, as far as we're concerned, will always be a combination of other standard forces that we've already studied, like tension in a string. You can provide the necessary force towards the center of the circle by having an object tied to a string and whirling it around, and there'd be a tension force that would be the force towards the center. Or it can be friction. I'll show you an example of that in a minute. Or it can be a normal force. I'll show you an example of that in a minute. Or it can be a gravitational force, when one body orbits another, such as Moon orbiting Earth. Okay, but this net force towards the center of the circle is going to come from standard forces we've already studied. And we'll learn next semester about another one called a magnetic force that will do this for us as well. Okay, but again, I'm just emphasizing. The net force towards the center of the circle is going to come from one or more of the standard forces we've already been studying. Now let me show you a picture and talk a little bit about just setting up Newton's second law problems that involve uniform circular motion, or circular motion. Because there's just something a little bit different that we have to deal with than we had in what's called rectilinear motion, i.e. motion along a line. So what my little drawing down here in the lower left shows, well, it shows an XY coordinate system. We're looking down from above on something horizontal, and that gray disk would represent maybe an object called a turntable, which is a little table that rotates about an axis right there through the center, coming out towards us, like an old-fashioned record player. Okay? And so this disk represents a turntable that can rotate, okay, either clockwise or counterclockwise, depending upon how it's constructed. And let's say that we have put on that turntable a little object. My drawing shows what it calls a coin. Okay? The coin, the arrow there points towards where the coin is at the moment we took this snapshot. But I'm imagining that this turntable is rotating, let's say it's rotating around counterclockwise as we watch it. And this is just a picture when we took a snapshot flash. And we want to apply Newton's second law to see how this particle, this coin on this turntable, can be moving in a circle. Because it will be moving in a circle, right? It will just be going around a circular path, roughly like that dashed curve I drew as the turntable goes around. So the coin sitting on the turntable is just sitting there. It's just going to go around in a circle, okay, of some radius from there to there, big R. And if we want to apply Newton's second law to understand how we can get that circular motion. Okay, so what I'm showing you, one of the things I'm showing you in this picture is the coordinate system that we're going to use, or part of the coordinate system that we're going to use for circular motion. Our axes, so far we've called our axes things like X and Y. Perfectly standard choice. For circular motion, it's convenient to make a slight change in how we talk about the axes we use to apply Newton's second law. And the axes are called radial and tangential. And I've drawn them here in my little drawing. I've drawn them anchored on the coin and pointing in the direction of the positive axis. So there's a radial axis and a tangential axis. Okay? There's the radial axis right there. And it's anchored on the coin at its current location, and all it does is point towards the center of the circle. The radial axis that we will take always points towards the center of the circle. The tangential axis is perpendicular to the radial axis and tangent to the circle. Hence it's called tangential. We'll also often have what I call a vertical coordinate, which in this case would be perpendicular to the screen pointing straight up towards us, because that's the vertically upward direction, and that will be handy too sometimes. In fact, let me draw another perspective of this situation, of the coin on the turntable. This is a top-down view of the coin on the rotating turntable. Now let me draw what I'll call a side view. From the side, the turntable, the disc of the turntable looks like that. And I'll draw a dashed line going through the middle and perpendicular to it. And that's called the axis of rotation. That's the axis that the turntable is turning about. Okay? And sitting on that axis, at the moment we took the picture, so to speak, is this coin. There's my representation of the coin. It's just sitting there. I haven't done anything weird to it, like glue it down or anything. I'm just letting it rest on top of the turntable. Okay. All right, I want us to draw a free body diagram for this coin. Now remember, the turntable is rotating counterclockwise as viewed from above. Okay, and the coin is just riding right on the turntable. So the coin is moving in a circle like I showed in the picture on the left. But now I'm looking at it from a side view, and at the moment I took this picture, you have to understand visually, the coin was traveling directly into the screen, directly away from me as the viewer. But now let's draw the free body diagram. All of the forces acting on the coin. Remember, from Newton, if this coin is moving in a circle at constant speed, and that's what we're assuming, therefore it has an acceleration directed towards the center of the circle, therefore it must have a net force towards the center of the circle. There has to be some force on the coin towards the center. And let's be clear where the center is. Okay? Again, in my side view, at this moment, there's the coin. The center of the circle is right over there on the axis of rotation. If you like, to the coin's left from our perspective, right? To the left side of the coin, there's the center of the circle it's moving in. All right, here come the forces. Of course, we always have F grav. In the side view, vertically down would be drawn like so. So there's F grav, vertically down. Okay? You want to try the next part? Maybe you should pause the video and try completing the free body diagram for the coin, and then come back. Okay. All right. So, let's see. What else did you draw on the free body diagram? Well, the coin is on a surface, so there must be a force from the surface that's perpendicular to the surface, and we know that's called a normal force. So that has to be vertically up. Let's label it F normal. And as the coin goes around in a horizontal circle, there is no vertical motion of the coin up and down. So there is no vertical acceleration. So there can't be any net vertical force. So I know that these two forces, F normal and F grav, just balance each other. So that's the story for the vertical direction. But that can't be the whole free body diagram, can it? Because the coin is an acceleration towards the center of the circle. In this case, that's to the left of the coin for this picture. So there must be a net force to the left. What's that force from? Well, it's still coming from the surface of the turntable, but now it's parallel to the surface. The force from a surface that's parallel to the surface is called friction. So it must be a frictional force that's acting on the coin directed towards the center of the circle. Now here's another part of this that's interesting. Remember from an earlier video lecture, there are two kinds of frictional force, so-called static frictional force and kinetic frictional force. Which is the appropriate frictional force, static or kinetic? This one is subtle because it's very tempting to say kinetic frictional force because the coin is moving. But what's important for a frictional force is if there is any relative motion between the object that's resting on the surface and the surface. But in this case, the coin and the surface are moving around together. And the coin, it is assumed, is not slipping relative to the surface itself. It's just riding on the surface. So there is no relative motion between the coin and the turntable. So the appropriate label for the frictional force is little f sub s, static frictional force, directed towards the center of the circle. Let me add my axes. I'm going to draw them a little bit over to the side just so I don't get a cluttered picture. The radial direction points towards the center of the circle, As far as the coin is concerned, in this drawing, the center is to the left. That's why I drew the radial arrow to the left. The tangential direction is tangent to the circle. That would be, in this case, into the screen. The tangential direction is into the screen. So I'm not even going to try to draw it. But then there's a vertical direction, whoops, straight up and down. There's radial. Like that. There's a vertical direction. You can label that axis however you want. I guess I would label it in this case Z, since I haven't used Z yet. But that's vertical is the point. So in this case, it's the Z forces that balance, F normal and F grav, or Z forces. And it's the radial force that's giving you the circular motion. Now, when you actually apply Newton's second law to this scenario, you start, please note, you start right there. You write down Newton's second law by components, and the most important component is the radial component for circular motion. That is the prime coordinate, radial. So here's how I write Newton's second law for the radial axis. A radial equals F net radial over M. Just like I would have said, A sub x equals F net x over M. Now my coordinate is the radial one. The next thing to remember is what we wrote just up above. Our radial acceleration is our old friend v squared over the radius. The radial acceleration is towards the center, and its magnitude is v squared over r. So for the a radial part of Newton's second law, you can put in v squared over radius. Now on the other side, there must be a net radial force, and that's what goes on to upstairs, and then you divide by m. In our case, the net radial force comes from F static. All of the magnitude of F static is in the radial direction. So plus magnitude of F static over m. And that's all I can do at this point. I've just set up Newton's second law for the coin on the turntable. I can't go any further without additional information about the situation. I just want to show you here in this scenario our first application, or at least setting up, of Newton's second law for uniform circular motion. In this case then, the required force towards the center of the circle came from friction, static friction. But there are other ways to get a net force towards the center of the circle, other than friction. Let me show you one. Hopefully this will work. Okay. Here, when I run this, it's just a video that we made in the department. It's just a small sphere that's going to be rolling around on the tabletop, confined to the inside of a metal ring. And we're getting it moving pretty much at a constant speed around and around. So now the question is, first of all, what's the free body diagram? Well, let's focus on what's the force towards the center of the circle. If that sphere goes around and around in a circular motion at constant speed, then its acceleration is directed towards the center of the circle. So the question is, what's the force that's being provided? What's the force towards the center? You have to have that if you're going to have uniform circular motion. Think about that for a moment. Maybe you pause the video, but did you decide what is providing the force on the sphere towards the center? It's that ring that's in contact with it, yes? That must be the force towards the center. Think of that ring as a surface. So guess what? It's a force that's perpendicular to the ring at that point, perpendicular to the surface. The physicist would call it a normal force. Okay? All right, let me see if I can get to that video and run it so that you can see it. All right, now we'll slow it down for slow motion. It's just moving in a circle at constant speed. We're going to lift up the ring. Aha! Did you see what it did? I'll pause. Let me get you ready again. It's going around in a circle pretty much at a constant speed. So we have uniform circular motion. There must be a net force towards the center. It's coming from the normal force of the ring. What will happen if we lift up the ring and take it away rather quickly? We'll no longer have that normal force, right? So we can no longer have uniform circular motion. So we'll have motion in a straight line at pretty much constant speed. And up it goes. And then it just went straight off, tangent to the circle that it was moving in. Right? Okay. So there we had a situation where the normal force provided the force towards the center. And when we took that normal force away, the circular motion stopped, and it just moved in a straight line. Okay? All right, here's another application. All right? Something that we haven't talked about before. But here's a model of a commercial airliner, an airplane. And let's just imagine an airplane in flight. Let's just imagine it flying what pilots call straight and level. So traveling horizontally relative to the ground, not climbing or descending or anything, and at a constant velocity. Turns out, in that case, there are 4 balanced forces on the airplane. Of course, F grav down. There's a forward force from the thrust of the engines. There's an air resistance force called drag. We haven't talked about it in this class, but you know that in reality on things like airplanes, you cannot ignore that force. That's opposite to the direction of motion. So if you're flying straight and level, the forward thrust force and the backward drag force balance. What balances F grav downward? There better be something. It comes from the wings, of course. It's called lift. That's up. Okay? Basically perpendicular to the wings. And those balance. What if the plane wants to wants to turn in a circle, so as to change its direction? How does it do it? I gave it away. The pilot has to bank the airplane, tilt along an axis, along the length of it, rotate it, so that the wings are no longer level. That's called bank. Okay? The wings are no longer level. Now the lift, which is always perpendicular to the wings, okay, the lift has one component vertically up, which can still balance F grav, and then another component pointing this way, and then that's the way it's going to turn in its circular arc. Okay? So the force towards the center, my point is, in an airplane, comes from a component of the lift force from the wings. So this force towards the center, depending upon what's going on, can come from any of a number of different situations. Here's even another one that I want to show you. This one is one of those giant swing rides in an amusement park. And why isn't this working now? So I've messed this up somehow, haven't I? So bear with me just a minute. So I'm not sure why okay, maybe now we're okay. Now I think we're okay, aren't we? Yes, there we go. All right, I want to show you one of these giant swing rides that you probably have seen at an amusement park. Okay? All right. I'm just going to run this YouTube video. And that's the name of the ride. There it is. It's a very tall, something like a 40-story building. And people sit in these swings on the ends of cables, which are on the ends of arms going out. And they take them up very high and then turn them in a circle. Okay? All right. Now, I just want us to analyze the circular motion part of what we see here. Okay? Yeah, this gives me vertigo as I watch it. Okay? I'm scared of heights, so I wouldn't do this. There you go. I just told you I wouldn't do it. Okay? But some people think this is fun. So I want us to analyze this motion. Okay, that's what I want us to do. Now let me get back here. It's a number of different. Here is my very schematic drawing of what I just showed you. I've got the central pillar of the ride, okay? And then coming out of that is an arm horizontally of length D, and then tied at the end of that arm is a cable or rope or whatever you want to call it. Let's give it a length L, and then this particle at the end of the rope represents a person riding. Okay? And the whole thing is turning around, as you can see by that arc. So this person at the end of that cable of length L is moving in a horizontal circle parallel to the ground. Let me try to represent that circle very roughly there in my drawing. Okay? The person is moving in a horizontal circle. And notice there's the center of the circle. And there's the edge of it. So that distance right there is the radius of the circle. Now notice also, and you can see it in the video, that when we were in circular motion, the cable that hangs down normally and has the person sitting in at the end of it, is swung outward and makes an angle that I've marked here, theta, with the vertical. That dashed line is just to help you see that the cable of length L makes an angle theta with the vertical. And we'll talk about why it has to be that way because of Newton. Okay? But that's just the geometry. There's that boom arm sticking out of length D, and then there's the cable of length L with the person at the end of that cable, and that cable makes an angle theta to the horizontal, and the person's going around like this in a circle of radius r at a constant speed v. And what I want us to do here, using Newton's second law, is to find an expression for the speed v of the person's uniform circular motion in terms of d and L and g and theta. In other words, we could use that video, and if we had video capture software, we could estimate the length d and the length L and the angle theta, and then we would be able to calculate how fast they were going around. That's what I want us to do. Okay? All right, so let's kind of do that together. We'll start with a free body diagram. Okay? Obviously the system, we have to pick a system. It's that person. That's our particle. Okay? Right there. That's our system, the person. Moving with uniform circular motion in a horizontal circle of radius r. All right, I'm going to draw the free body diagram over here to the side. But it applies to the person at the moment that this figure has been drawn. By the way, at the moment this figure has been drawn, the person's velocity is into the screen, going directly away from us. We're drawing a side view. All right, let's try the free body diagram. You should do it first yourself, okay? Pause the video and draw a free body diagram for the person at this moment. Remember, the center of the circle at this moment is due left of the person. Okay? Okay, draw the free body diagram. All right, did you give that a try? I really hope you did. So if the person, at the moment we're drawing this, is traveling in a circle, moving directly away from us into the screen, with the center of the circle to our left, then there must be a net force to the left, right? Towards the center. All right, let's list the forces. Of course, F grav is always vertically down. Force due to gravity. What else? Interesting. Did you say a normal force? Don't feel bad if you did. A lot of people do. But guess what? There isn't a normal force on the person. Now, I'm thinking of the person, if you like, it's the person-chair combo, okay? It's just a blob at the end of that cable. And that blob, that person and chair combo, maybe that wasn't clear for you, that person-chair combo is not resting on any surface. You see what I'm saying? Unlike, say, the coin that I just talked about, which was resting on the surface of a rotating turntable. This blob at the end of this cable is not resting on any surface. That's what I mean when I say there's no normal force. What is the only thing that's actually touching this person-chair blob? It's that cable of length L, right? And what's the name for the force from a taut cable? Tension. And cables can only pull. They can't push. So the tension force from the cable has to be pulling up and to the left. In other words, along the direction of the cable itself. And then we'll label it T arrow. That's it in terms of forces. Yes, I'm ignoring air resistance drag force in this case. That's all I'm talking about. F-grav and tension. Okay? Now, let's get our axes in there. Remember, for circular motion, the most important axis is called the radial axis. You can draw it kind of wherever you want. The key thing, though, is to get the direction. If the person is where we see, and the center of the circle is where we see, then the radial direction is from the person towards the center, which in our case would be to the left. The tangential direction is tangent to the circle. In our case, that'd be into the screen. I'm not even going to try to draw it. It's not important. But then the other important direction, in this case, is vertical, vertically up. I'm going to call that Y. You can call it Z if you want. The point is it's vertically up. There are my axes, okay? Now, if you want, we could also break down our forces into components for these axes. That would be helpful. F-grav is completely vertically downward. But the tension force, notice, has a vertical component and a radial component. Let's sketch them both. Okay? Let's draw the component triangle for the tension. There's the radial component of the tension, and there's the vertical component. And that angle right there is a right angle. Oh, and I also know that this angle up here is the angle theta that the cable makes with the vertical. Okay, it's very important that you see that. How we do that free body diagram? That we chose axes, radial being the most important, then the second most important being vertical, and then how we drew a component triangle for the tension force. Notice now then where the force towards the center is coming from. It's coming from the radial component of the tension, right there. But let's write down Newton's second law in component form, okay? And our two components are radial and vertical, or Y. So I'll start writing them over here. A radial equals F net, comma, radial over M. Let's start with that one. Now for A radial, we have our good old friend V squared over the radius of the circle. So I will go ahead and write that. That's the left side of Newton's second law. On the right side, I need F net radial, and then I divide by M. I just marked, bring it back down, the only radial force in the free body diagram with the little red check mark. It's that radial component of the tension force. So that's what I've got to write down. Now I got to be able to get that component correctly from the component triangle, and notice that component is opposite to the angle theta. So I would take hypotenuse times sine theta, and the hypotenuse means, in this case, the magnitude of the tension force, and it's in the positive direction. So magnitude of tension force times sine of theta. And I have applied Newton's second law for the radial component. And there's nothing more I can say with that right now. Okay? So I'm just going to number that equation, number 1, and say that's going to be useful, but I'm going to need another equation. Where's that other equation going to come from, I wonder? How about applying Newton's second law for the other coordinate here in the drawing, the y coordinate? Let's do that as well. Let's write it over here. A sub y equals f net comma y over m. Now, again, the particle is moving in a horizontal circle at constant speed. There's no vertical motion, and we're not worrying about that part that you saw in the YouTube video where it's going up and down. Don't worry about that. It's an interesting complication, but I'm not doing that now. Horizontal circle. No vertical motion at all. So I know from the physical situation I'm studying that there is no y acceleration. A sub y equals 0. So I conclude from Newton that the net y force on the particle must equal 0. So I just need to get all the y forces and add them up and make them total 0. Where are the y forces in the free body diagram? Well, there's of course F grav with all of it being negative y, and then there's this y component of tension being positive. And those two end up balancing each other. So let's write down that expression. Okay? All right, just let me move this up just a little. That's enough for now. All right. Upward, I have the y component of the tension. Let's be careful. That would be magnitude tension cosine theta, because the y component of the component triangle for tension, the one marked with the black check mark, is adjacent to the angle theta. So hypotenuse times cosine theta. Then minus the entire magnitude of F grav. And that must equal 0. Okay, now I'm going to push this up a little more, because I'm pretty much done with the free body diagram. Let me remind you of the canned formula for the magnitude of F grav. It's the mass of the particle times little g. So that's what I've got here. And that's what I'm going to use. Okay. All right. So, magnitude t cosine theta minus mg equals 0, or how about like that, equals mg. Now that's a second equation, yes? Now I've got two equations. That'll be enough. Remember, my goal is to find an expression for v. How fast is the particle moving around in its horizontal circle? I couldn't just stop with equation 1. You see why, and claim I had my answer? I couldn't just solve equation 1 for v and say, I'm done. Do you see why that's not acceptable? The problem said I'm allowed to have the answer for v in terms of the following stated symbols: the distance d, the length l, little g, and the angle theta. Equation 1 has all kinds of other stuff. So I'm not done. But what I can do is use these two equations to get rid of something unknown that I don't want, like the tension magnitude in that cable. So let's solve equation 2 for the tension magnitude. That's not hard. Just do your algebra on equation 2 and solve for T magnitude. You get T magnitude equals mg divided by cosine theta. And now substitute this expression into equation 1, where the t is. So now what I have is v squared over r equals. Now for the t, I'm going to write it like this. Group things with parentheses. mg over cosine theta. That's the magnitude t part in equation 1. And that's multiplied upstairs by a factor of sine theta and divided by a factor of m. You see, all I did was substitute the expression for t into equation 1. But now, some good things happen. Like the mass, m, is upstairs and downstairs and cancels. I don't need to know the mass of the person and chair blob at the end of the cable. Doesn't matter. And the equation then on the right simplifies to g times the tangent of theta. So now let's solve for v. How fast is the person, chair, blob moving? So I multiplied both sides by r. So I get rg tangent theta. And take the square root, right? Because it was a v squared. Now I'm almost done. But the problem told me what my answer v can depend on. And r is not one of those symbols. R is the radius of the circle. But a quick look at the picture, again, reminds me or points out to me that I can express the radius r in terms of d, l, and theta. Do you see that? That's just some geometry and trig there. From that picture, I can see that the radius of the circle, r, is the length d of that horizontal arm coming out, plus this part right here that I just drew in red, which is the length L times sine theta. Okay? All you gotta do is look at the drawing and use some geometry and trig. You should be able to convince yourself that the r is equal to d plus L sine theta. So with that in mind, all I do is go back up here, and where the r is, I put the combination d plus L sine theta in parentheses. Then that's multiplied by g and by tangent theta. And I have found my expression for the speed at which it's going around. I need to be able to measure 3 things on the YouTube video. The horizontal length d of the arm that's coming out, the length L of the cable, and the angle theta that it makes with the vertical. And then I can just plug into this formula, and I will be able to then get for you how fast it was going around. Okay, so there's an application of Newton's second law to a real-world situation involving uniform circular motion. Okay, I'm hoping that these are helpful. We'll be doing another application in the next class video. But for now, I'm going to leave you with a class engagement exercise that you will answer on Blackboard. Okay, here's the scenario. There's a coin, such as in the figure below, there it is, see it, riding without slipping on a horizontal turntable that rotates at a constant rate about an axis through its center. You're looking down from above on the rotating turntable, and we're shown that it's rotating counterclockwise. The coin moves with uniform circular motion, at least for the first parts of this problem. The figure shows a top view of the coin and turntable at an instant in time. Okay, here are the questions to consider. A, which of the 8 labeled arrows in the figure, you can see they're labeled A through H, you can see which way they point, which of the 8 labeled arrows in the figure represents the direction of the velocity of the coin at the instant shown? So when you go into Blackboard, you put A, part A, and then you put a letter, capital A through capital H, for the correct answer. Part B, which of the 8 labeled arrows in the figure represents the direction of the acceleration of the coin at the instant shown? But if the answer is acceleration is 0, just enter 0 for the answer. Part C, which of the 8 labeled arrows in the figure represents the direction of the net force on the coin at the instant shown? The answer is 0, enter a 0. Now part D, I will warn you, is a little bit tricky, and it is expressly not uniform circular motion. Here's what's happening in part D. Which of the 8 labeled arrows in the figure best represents the direction of the net force on the coin at the instant shown? Fine. If the turntable is speeding up in the direction of rotation, still assuming that the coin does not slip relative to the turntable. So that would be the case, for example, when you first turn the turntable on, because initially it's at rest, and it has to speed up to its final rotational rate. So here we're talking about the case where the coin is moving counterclockwise in a circle and speeding up. What do you think is the best choice for the arrow for the direction of the net force? That one's a little bit of a challenge. Just see if give your best shot at it. Okay? All right, so that's our class engagement set of questions for this video lecture. And that's all for right now.